this class of therapeutics called Senolytics seems to be, there's a lot of buzz around it at the moment. So what are Senolytics and why are they something that the aging field is excited by?
Yeah, it's a great question. I'm going to zoom absolutely right out to give you an answer for this one. I know that you and Matt talked about this idea of the hallmarks of the aging process. And these are something I talk about in my book. I've got 10. There are, people will give you different numbers, and there's actually been a new paper just released which would bring the total to 12. I think some of those are incorporated in some of mine, but it depends on the day of the week, exactly what's included. But what are these hallmarks fundamentally? They are changes that happen inside our biology, inside the biology of other animals. And first of all, they're things that change with age. Obviously, something can't be, causing the aging process if it doesn't change with age. And they're things that if we in the lab increase the rate of that change, we can increase the rate of aging, we can reduce lifespan, we can increase disease. And if we decrease that rate of change, it seems to slow down what we'd broadly define as the aging process. And that's how something gets classified as a hallmark. So they're sort of potential causes of aging. Because they change with age and because changing them changes aging, it seems as though they could be causal. We don't know yet because we don't know exactly how these things all link together, but that's the idea. And there are a variety of these different hallmarks. They start at the very, very sort of tiny level, the molecules, things like changes in our DNA. So we can get DNA damage, we can get mutations happening at the very smallest level inside cells. And then as we sort of magnify up, we can go all the way up to changes in whole systems in our body. So things like the immune system, dysfunction of the immune system. So we get less good at fighting disease. Our immune system gets less good at rooting out cancer cells, and so on and so on. And that gets worse and worse as we age as well. And in between these two scales, slap in the middle of the hallmarks, I put them, the accumulation of what are called senescent cells. And these are cells that were actually first discovered way back in the 1960s by a guy called Leonard Hayflick. And he was watching cells called fibroblasts that are just dividing in a dish. And he noticed that if he let them divide and divide and divide, then after about 50 cell divisions, something very strange happened. So the first thing is that the cells just stop dividing. But the second thing is, and I am by no means a cell biologist, by no means a microscopist, but you can see that there is something wrong with these cells. He called it the fried egg phenotype, because these cells go from these sort of lovely, sort of ordered looking roundish objects to this splat. They've got this really weird exterior shape. You can just see there's something very, very strange going on with these cells. And so they stop dividing, they've entered this strange state. He called it cellular senescence. We've already met that word senescence because it's just a biological term for old. So he thought these cells were just becoming old, and that's something that's going on certainly in cells in a dish. The question is, does accumulation of these cells in actual living, mice and actual living people drive the aging process itself? And it took us a very long time to get to the point where we could answer that question, but I think it was convincingly starting to be answered in the 2000s. We noticed that these cells do indeed accumulate in humans, in mice, and so on. And there are a variety of different reasons a cell can become senescent. So the crucial thing about this senescent state is it's non-dividing. And so the first reason that a cell can become senescent is that it gets a lot of damage or mutations in its DNA. Now, what are mutations? They're mistakes in the genetic code, essentially. And if a cell accumulates the wrong combination of mutations, that's how cancer starts. So if a cell's got this combination of mutations, it can learn to divide and divide and divide indefinitely, and that becomes a tumor, and that can obviously go on to kill you. So our bodies have got a number of mechanisms to try and stop that from happening, and one of them is cellular senescence. So if there's a load of damage to the DNA, the cell's looking a bit fishy, then the body just slams on the brakes, puts it into this senescent state. You can also get cells that are senescent because they've divided too many times. We've already talked about that because of the Leonard Hayflick's experiments. That happens in our bodies too. And finally, you can just get cells that are stressed. They're in a sort of stressful environment. I don't mean stressed in sort of the day-to-day, my job's stressful sense. I mean that in the molecular biology sense of stress. So there's stressful chemicals essentially going on, inside the body. So cells can enter this senescent state for a variety of reasons. And when we're young, this is happening all the time. You and me have got plenty of senescent cells in us right now as we have this conversation. But because we are relatively young, I guess, then what's going on is that these cells enter the senescent state and they start spitting out this variety of different molecules. And what the molecules are doing is they're saying, hey, over here, I'm senescent. You might want to come and clear me up. And the place that they're signaling, of course, is the immune system. So an immune cell will sense this chemical cocktail. It'll dash over to the senescent cell. It'll gobble it up. And that's just a way of getting rid of that senescent cell. And so once that senescent cell is gone, it's not a problem anymore. And that whole process can continue. So all the time in our bodies, as we're young, those senescent cells are being produced and the immune system is clearing them up. But the problem is, as you get older, these processes, they change fundamentally. So you can start accumulating more of these cells. There are more cells with DNA damage. There are more cells with mutations. There are more cells that are in a stressful environment. There are more cells that are divided too many times because that's what they do during the course of their cellular lives. But also, the immune system is getting less effective. I already mentioned that's another of the hallmarks of aging. And so it's getting less good at responding to these signals and less good at clearing up that those damaged cells. And what then happens is that this it's called the SASP, the senescence associated secretory phenotype, which is a hell of a mouthful. Senescence associated is associated with these cells. Secretory, they secrete them, so they sort of give out these chemicals, and phenotype is just biological word for thing that happens. So biologists do like to give things sometimes slightly overcomplicated names. But this SASP, it's essentially the hey, over here, come and clear me up immune system signal. But unfortunately, when these cells start to accumulate, that can essentially become something that accelerates the whole aging process. It can drive this process called chronic inflammation, which is a sort of hyperactivity of the immune system that contributes to aging. It can make cells become cancerous, ironically. So something that started out as an anti-cancer mechanism can actually cause cancer in sufficient quantities. And finally, it can actually even induce senescence in surrounding cells. So it's got this sort of snowballing type effect that means that it can get worse and worse and worse with time. And so this does seem to be a very obvious candidate for a cause of aging. It's something that accumulates in our bodies as we get older. It seems to drive a whole range of age-related diseases. So that might be quite a depressing story, but there's some really, good, exciting news at the end of this story. And the reason we can be so sure that these things do cause age-related diseases is because scientists have come up with drugs that can remove these senescent cells while leaving the rest of the cells of the body intact. And I think the most compelling evidence for this is a paper that came out in 2018. Scientists gave these drugs to mice that were, I think, 24 months old, so that's sort of 60, 70 years old in human years. And they found that they basically, I'm happy to say, made the mice biologically younger. So they removed the senescent cells, that's a good thing. They find the mice live longer, but they're not just staggering along, with their frailty extended somehow at the end of their lives. They get less cancer, they get less heart disease, they get fewer cataracts clouding the lenses of their eyes. They can run further and faster on the tiny mouse-sized treadmills they use in these experiments. They seem to reverse some of the cognitive decline that comes with aging. So if you put a young mouse in a maze, it's often very excited to explore its new environment, find the food, whatever. But an older mouse might be a bit more anxious. Maybe it's just a bit less physically active, and so it doesn't want to go and explore. But by removing some of these senescent cells, you can rejuvenate some of that youthful curiosity. And finally, it's really worth, if listeners haven't seen a picture of these mice, again, I'm not a mouse biologist, I don't play with mice in the lab regularly, but nonetheless, you don't have to be an expert. You can see the mice that have had the drugs, they look fantastic. They've got much better fur, they've got thicker fur, they've got less grey fur, they've got plumper skin, they're less fat than the mice that have not been given the drugs. So it seems to have really this absolutely almost global effect on the aging process. And that's hugely exciting because I think this is the paradigm that we want to, have going forward, is finding a hallmark of aging, identifying a way to change that hallmark of aging back to a more youthful state, and then potentially preventing a whole range of different diseases. And so now we're at the stage where these things definitely work in mice. We've got really, really strong evidence that senolytics have an effect in mice. And so the next step is human trials. And we've already talked about this process in the sense that these senolytics aren't being trialed. We aren't just giving them to 50-year-olds who've accumulated senescent cells throughout their lives and, preventative for an aging indication. We're now using these drugs for people who've got very serious diseases. So there's a disease called lung fibrosis, which is very common in older people. And senescent cells are often found hanging around the site of this fibrotic, so effectively scarred lung tissue. And so the idea is that by giving people who've got this disease that doesn't really have any great treatments at the moment, this sort of ray of hope with the senolytics, hopefully we can prove that they work. We can see that the senescent cells get removed. And the thing that I really hope is not only that obviously the drugs work, that people get better, but also that the side effects are relatively mild. Because what that means is if there's a good side effect profile, we can then say, okay, these drugs don't have many side effects. Let's try giving them to people with, late stage heart disease. That's another thing we know that senescent cells are related to, but it's something we already have drugs for. We already have diet, we already have a variety of ways we can help people who've already had a heart attack, for example. And then again, if it's safe in that population, we can spread it wider and wider still. So this is a super exciting thing because hopefully we'll know the answer to the more severe diseases within the next few years. And if we can carry on widening that net, it's probably not going to be, more than 5, 10, 15 years before we can start thinking about using these things preventatively for aging.
And when you say drugs, we're talking here about senolytics. And do these senolytics or compounds, are these typically, or are they always polyphenols like fisetin and quercetin, or are these just certain types of senolytics and it's a much broader sort of category?
It's a really interesting field, actually. So the way that the reason quercetin comes up so much is because in this 2018 paper, actually, but also in a lot of other papers from that group, in the original paper where they identified the first senolytic drugs, The way that they worked this out was they got a whole bunch of things that they thought might have some effect on senescent cells. And then they just got a bunch of cells in a dish and dripped various combinations of these drugs onto the cells in the dish. And they found the drug that killed the senescent cells but left the bystander cells relatively unaffected. And in the end, after having tried a whole load of not just individual drugs, but as I said, combinations, they found that the most effective combination for killing senescent cells was quercetin, which is a flavanol. It's found in various fruit and veg, but it's also plus dasatinib, which is a chemotherapy drug. And it's important to say this is at much, much lower doses than you'd normally use it in cancer. But they found that this combination somehow got in there and effectively convinced those senescent cells to kill themselves, convinced them to go back onto the sort of cell suicide pathway where we'd very much hope they should have stayed. So I think some of the sort of hype around quercetin has come because it was found in that context. The real question that we don't know the answer to is at what dose and in what context. Does quercetin on its own at a particular dose have the same effect in humans that it plus dasatinib had in mice? And I think that's a really big question. There are some other flavanols that are being investigated as well. There are other actual drugs. But I think the sort of long term of this field is going to be finding much, much more powerful and specific senolytics. The reason that dasatinib and quercetin end up being used is they're effectively off-the-shelf compounds. So these scientists were trying a bunch of stuff that they had access to in the lab. But hopefully now we understand that senescent cells are important and that senolysis does seem to have positive effects, then we're going to go out and find specific drugs designed to be senolytics rather than just some flavanols that seem to happen to have that effect. And so maybe, that's an argument for eating certain kinds of fruit that have the quercetin in it. It could possibly be the case that quercetin supplements are useful. But I think the more exciting prospect is a little bit further into the future when we come up with drugs and other interventions that can kill the senescent cells. And it's worth saying these things might not even be drugs. They might not even be supplements. There are some people who come up with a vaccine for senescent cells. So you effectively teach the immune system to go after these cells a bit more effectively in older age. There are also, there are peptides. There are just a variety of different compounds and approaches. There are probably going to be gene therapies again to kill these senescent cells. So it's a really, really fast moving field. And I'd be very surprised if it turns out that these flavanols are, even in the top 10 when the dust settles and we've got the best treatments.
So is it worth taking any Senolytic supplements now? I know there's a few brands that are kind of selling them at the moment or claiming that they have ingredients that have sort of Senolytic properties. Is that kind of worth the cost at the moment, or are we better off just eating a healthy diet?
I think we just don't know. I think the way that I sometimes look at these things is, you find some foods that have got quercetin in that you quite like anyway and try and maybe amp that up slightly in your diet. It might not be a clinically relevant dose. That's often the case with these things. Like we know about resveratrol. If you eat grapes or drink wine, you have to eat a ton of grapes and drink 25 gallons of wine a day in order to possibly get anywhere near something that might be a clinical dose. But I think that really, we just haven't got the evidence for these things, and it's frustrating. What we need to see is these randomized controlled trials, or at least some kind of trial in humans. And one of the big challenges is that we're not even very good at counting senescent cells yet. We don't have a really firmly agreed upon definition. Some scientists say it's due to expression of certain genes. Some other scientists might use something that looks for a particular protein in the cells, and so on and so on. But there isn't even a firm agreement on what exactly constitutes a senescent cell, which means if you want to do a shorter term trial where rather than looking at lifespan, which obviously takes ages, you instead look, does this thing remove the senescent cells? You're going to find a room full of scientists arguing about what exactly constitutes a senescent cell. So I think luckily we're in a place. This is hugely exciting. There are startups. There's big money going into some of this stuff. Unless you're already very old and willing to take a risk on these things, I just watch and wait because the evidence is going to be coming in very, very soon.
Eat your apples in the meantime.
Damn right. Keeps the doctor away. That's what I've heard.